Okay, so you can clearly hear me, right?
Yes, sir.
Okay. So let me introduce myself. I am Moina Ghoshal. I am doing PhD at Indian Institute of Science, Education and Research, Kolkata, ISER Kolkata, and I'm a PMRF. And I have been assigned as a TA for this course NOC 23CY09, for which the instructors was Professor Sayan Bakchi and Professor Anirban Hajra. And this is the assignment related to week 3, where I am going to solve some problems related to week 3 lectures that will help you to solve your assignment problems. So I am going to solve some dummy problems that will give you some hint so that you can easily solve those. Okay, so first, basically, what was what I have discussed in the past 2 weeks, that what is spectroscopy and what is a spectrum. This was the beginning. Okay, so this was the beginning, that I have explained what is spectroscopy and what is a spectrum. Why we need spectroscopy? Because I have mentioned that wherever you go to characterize anything, to give a proof of something what you can think of, you need spectroscopy. Okay, then we have introduced this term, this light matter interaction. Okay, where there was two schools of thought. One thought that light is a particle, one thought that light is a wave. So from that, the concept of wave particle duality came, and then Einstein's AB coefficient concept came, where three different phenomena were observed. The three phenomena are actually the concept of absorption. You know, absorption. This is the excitation of the molecule from the ground state to the excited state. Okay, this absorption. Then there was stimulated emission, for which you need light source, which light will stimulate the emission process, and another is spontaneous emission, which happens without the need of any light source. It happens spontaneously. And then Professor Anirban Hajra has explained the postulates of quantum mechanics, where he has explained the concept and properties of wave function. What is a wave function? How can we? And he has clearly compared the classical picture and the quantum picture. From whatever you see in classical mechanics, for everything there is an operator in the quantum mechanics. He has also explained that, and from then he has explained this time-dependent Schrodinger equation, and also to explain such phenomena, a simple quantum model was taken, which was particle in a box. And for this, the wave function energy all was calculated. It was shown that how it is varying with the quantum numbers. And then the selection rule for electronic transition came, that under which is the selection rule for this electronic transition. And then it was seen that for an electronic transition to happen, what is needed, that your transition moment integral should be non-zero. There was a concept of transition moment integral. Okay, just a minute.
Yes, sir.
Yeah, so there was a concept of transition moment integral, which was shown to be not equal to zero. Then your transition can happen. And then interaction of the electric field of light with matter, how they are interacting, you have seen that the time independent Hamiltonian became the time dependent, because your electric field is time dependent. And then the condition was found about the intensity of transition, and what condition you could get more intense transition, and there the condition of Bohr frequency condition was evolved. What is Bohr frequency condition? Bohr frequency condition says that the energy difference between two levels, suppose my upper level is E2 and lower level is E1, that should be h nu, that is the energy of the light. This is the Bohr frequency condition. Under this condition, your intensity of the transition will be maximum. And then different types of line shape functions was introduced, like Gaussian function, Lorentzian function, what is a void function, and also concept of different types of line broadening, like Doppler broadening, pressure broadening, collisional broadening. Different kinds of broadening was explained. And also the different types of spectroscopic techniques which uses these from this electromagnetic spectrum, under which time scale that they are going, also they were discussed. And also there was a derivation of Lambert-Beer's law, which is related to absorption. Okay,
Yes, sir.
yeah, there was a derivation of Lambert-Beer's law, which says that absorbance nothing but equals to epsilon C into L. So what is epsilon? Epsilon is called molar extinction coefficient, and C is the called concentration, and L is the path length. And then concept of Born-Oppenheimer approximation was introduced, which tells that you can consider this electron and nuclei motion separately. So this was about the last 2 weeks assignment. So in this week, what Professor Sayan Bakshi has given lecture on about angular motion. Okay. So angular motion, this was the start beginning of this week's lecture. This angular motion. 1 minute. Yeah. This was the beginning of this lecture. This angular motion and how it is related to the linear motion. From linear motion, you can convert anything to the angular motion. How they are related, and from then the concept of moment of inertia. From this comparison, the concept of moment of inertia was introduced. Okay, so what is moment of inertia, how it is related in angular motion, and to what quantity in linear motion it is related to, that was explained clearly. And then the calculation of energy of rotational energy levels were calculated. Where should be the energy, how it is dependent upon rotational quantum numbers, all there were introduced, and also the concept of rotational quantum numbers also introduced. Then in the next lecture, there was a condition to found that for a molecule to be IR active, what should be the condition? The condition for a molecule to be microwave active or IR active, I've said wrong. This will be microwave active. Okay. So what should be the condition under which a molecule will be microwave or rotationally active? You have seen that these dipole moments would be non-zero. The change in the dipole moment should be non-zero. Just like your hydrogen, H2, C2, N2, different kinds of molecules, you can see that these are called homonuclear diatomic molecules, because since you know that this is a diatomic molecule because two atoms are there, and since two atoms are identical, so you can call them homonuclear diatomic molecule. And here, since the two atoms are same, there will be no dipole moment here. Okay, so that kind of molecule H2C2N2, it is will be microwave inactive. But whenever you are replacing this hydrogen with some another atom, like if you are replacing with H with the Cl, you can see that there will be a dipole moment, and hence ACl will be rotationally active. And then the concept and calculation of reduced mass was introduced. What is the reduced mass? Reduced mass is defined as, if I have two particles, two atoms which are joined and both have mass m1 and m2, you can write the reduced mass as this one, m1 into m2 by m1 plus m2. So this will be the reduced mass of the system. Then the selection rule for rotational spectroscopy was discussed, and here the concept of transition moment integral was also discussed. What is the transition moment integral? How transition moment integral affect the selection rule? And there it was proved that if J is the rotational quantum number, the selection rule will be J is equals to delta J is equals to plus minus 1. Only this transition where there is a change in the rotational quantum number by 1 unit from upper side or lower side, that will be only allowed. Other values of delta J will be not allowed. And there will be a problem in the next upcoming slides, and where I will discuss that again. And also finding the energy gap between two successive lines in the rotational spectra, that was also discussed. How can you find this rotational spacing between two line from the rotational spectra, and from that you can easily calculate what should be the bond length if you know the mass or reduced mass of the system or individual mass of the atoms. Then appearance of it was shown that there was a rotational spectra of carbon monoxide, where it was shown that for every individual peak there was a satellite peak with a very low intensity, and the difference between these two peaks is gradually increasing. So what should be the case, that was discussed in the with the idea of isotope, effect of isotope. Because or this, since this was discussed about this has discussed about carbon monoxide, so in that viewpoint I can say that for carbon has another isotope of other than C12, there is C13. Okay, so this also contribute, but the intensity will be very very small because its relative abundance is very very low. You know that. So there was the intensity of the peaks will be low, but there was how they are differing from this main peak, how they are changing with increasing the how their distance between interdistance between is gradually increasing. That was already discussed. And then in the 16th lecture, there was the concept of degeneration, how to calculate it, and this was explained. Degeneracy and how to calculate it. We have seen that degeneracy is given by 2j plus 1. So for every j quantum number, there are another 2j plus 1 states which have the same energy. And hence, concept of rotational quantum numbers mj and how it is related to this degeneracy of this rotational level, it was also discussed. Okay, so this was the outline of the whole week course what Professor Bakshi has taught, and now I am going to solve some problems regarding that. So this is my first question. So in which case transition energy between the ground and first excited state is highest? That means what in which case the difference energy difference is highest? Is it the electronic transition? Is it the vibrational transition? Is it the microwave transition or it is the radio wave transition? So what should be the answer?
Electronic.
Electronic, right? Oh yeah. Okay, so in which case you said electronic. Fine. So I'm explaining that using this energy diagram. You can see here that for each transition, each different transition, which range of electromagnetic spectrum is responsible, right? So you know that for electronic transition, which part is responsible? It is UV visible part. UV visible. Sorry. So UV visible part. So this electromagnetic part where this UV visible light is responsible for your electronic transition. So for vibrational transition, which one is responsible? Your IR mode. Okay. So your IR mode is responsible, or IR transition is responsible, which is also here mentioned as infrared transition. This is responsible for your vibrational transition. The microwave transition refers to microwave range. And also radio wave transition, you know from by this name, this is corresponding to radio wave range. Okay, so you can find this answer in also lecture number 11 or 12. Now you have chosen that what range of electromagnetic spectrum these transitions happens. Okay, now you have to find which one is higher in energy. So you can see this radio wave, and here I have shown a drawing where you can see that energy increases from left to right. That means your radio wave from radio wave to microwave to infrared to visible to UV to X-rays to gamma rays, energy is gradually increasing. That means microwave has greater energy than radio wave, infrared has greater energy than microwave, and vice versa. Okay, so you can see that. So I'm going from the downward. So radio wave, you can see where it is located. It is located here. Sorry. You can see that the radio waves are located here. Microwave This is the microwave. So I'm just writing by this. This is, since this is the fourth option, okay, I'm writing it as 4. Now this is the microwave region. This is the microwave, so I'm writing it as 3. Okay, you can see here that for microwave transition, microwave radiation is needed. Next, for IR transition, for vibrational transition, you need IR light or infrared radiation. I'm writing is at 2. And for electronic transition, you need UV and visible, like this one, this whole range. Okay, this is number 1. So you can see, as I am saying that from the left to right, energy is gradually increasing. So this UV visible will have higher energy. That means the electronic transition, which is related to this UV in the UV visible region, that will give us higher energy. So this is the explanation that electronic transition generally occurs in the UV visible region of the electromagnetic spectrum, and thus it is expected that it is associated with higher energy than the others. So the answer will be electronic transition. Clear? So is it clear?
Yes, sir.
Okay, fine. So I am moving to the next question. Which of the following in linear motion is analogous to the moment of inertia in angular motion? Is it velocity? Is it mass? Is it momentum? Is it kinetic energy, or is it mass? So what should be the answer?
Velocity.
Velocity. Okay. So I have what I have explained in the starting of this course content, that for in the linear motion, if you are converting it to angular motion, the quantities will be changed, and you can see the answer in also lecture number 12, that
Mm.
for linear motion with position, if you want to define some particle with position in this linear motion, in case of angular motion you need to define it with angle. If you want to define some particle with linear motion with momentum, you need angular momentum in angular motion. Similarly, if you want to designate something with velocity in a linear motion, you need to design it with angular velocity, that is omega. You will know this. So, suppose I am designating is a position as x. In angular motion, it is generally designed as theta. Momentum in linear motion, it is designed as, yeah, it is designed as p. In angular momentum, it is designed as L. Okay. In velocity in linear motion, it is generally given by v. This is not new. This is v. And in angular velocity, it is given by generally omega. Okay. Similarly, mass in linear motion, which is described by m, it is in angular motion. It is described by this term, moment of inertia. I. Okay. So moment of inertia in angular motion is generally analogous to the mass in linear motion. So your answer will be mass. Got it?
Yes.
Okay. Okay. So I'm moving to the next question. So you have to identify the correct relation. This L I have discussed in the last question. This L is the, what is L? L is angular momentum. What is r? Radius or distance, you can say anything, and p is the
Momentum.
momentum, exactly.
Linear moment.
Linear momentum, okay. Yes, you're correct. Linear momentum. Huh. Okay. So you can see the different, what is the relation between these, that L, R and P is, you have to find that, and then another relation is there. So which one will be correct, or one or more will be correct, right? Which one will be correct? Which should be the relation between L, R and P?
Last one. Mass of mass
This one?
into velocity. Yes.
Only this one, or one another will be there?
The third one also.
Third
Vector
one.
product will be same.
Third one. This one.
Huh.
No, these two are not same.
Okay.
Okay. So okay, I will
Yeah.
explain that. Okay. So you know your angular momentum. You can write this angular momentum as a relation L is equals to R cross P. This will be the cross product of your radius and linear momentum. Okay. Just when you are converting your velocity in linear motion to velocity in angular motion, you are just multiplying it with r. But here you are doing cross product, because it will depend upon the angle between this r and p. Okay, so you are defining this with your angular motion, you are defining this angular momentum with this relation, L is equals to r cross p. So one answer will be this one. But okay, so in case of vector, oh yeah. So in case of vector, you just remember this relation always, that when there is a cross product between two vectors A and B, this cross product, you cannot write this. Okay, these two are not equal. If suppose I with argue I can say that yes, these are two are equal in magnitude, but they will be different in directions. Okay, so in vector you cannot write that A cross B could be equals to A B cross A. So your, if your, it is your right answer that L is equals to R cross P, this is the correct answer. Just a minute. L is equals to R cross P is your correct answer, but this one L is equals to P cross R, this is a different quantity what I have explained here. That A cross B is not equals to B cross A. So your answer will be, one will be L is equals to R cross P. Now I can write this momentum. Now I am writing this again here. L is equals to R cross P. Now we know in linear motion, what is momentum? Momentum is nothing but mass into velocity, right? So I can write
Yes.
momentum in terms of mass into velocity. Now, if you are going to replace that, R cross, I am replacing this m with mass into velocity. Okay. Now, since m is not a vector quantity, mass is not a vector quantity. Okay. So you can remove this out of this. So my M will be there, and this will be the cross product R cross P. So if you find the angle or the cross product between the radius and the velocity, and if you are multiplying it with M, you will get your angular momentum. Okay, so this will be, so which one will be the answer? Another one, this one will be your also answer. M is equals to R cross P. But your fourth answer will be not there because R cross V is not equals to P cross R. So your this two will be your answer, that L is equals to R cross P, and L is equals to sorry, this will not be vector. Sorry for the mistake. This will be Im into R cross P. So these two will be your answers. Okay. Is that fine?
Yes, sir.
Yeah. Okay, so I'm moving to the fourth question. That it is saying that in a rotational level, 10th and 11th line are separated by a spacing of 20 centimeter inverse. We have to find the value of the rotational constant. So what will be the rotational constant? Your 10th and 11th line, two successive lines, they are separated by a spacing, and the spacing is 20 centimeter inverse. So what should be the value of rotational constant? So how rotational constant is defined? By which symbol? B. Okay. So your rotational constant is actually defined in terms of B. So you have to find the value of B. If you know what should be the relation between two successive lines or 10th or 11th line in terms of B, then from that you can calculate B, because if you know the formula from of the difference between 10th and 11th line in terms of centimeter inverse, how much centimeter inverse is there, so you can easily find B in centimeter inverse. So what is the formula? The formula is delta of delta nu. You know, yeah. Suppose this is my rotational lines. This corresponds to j equals to 0. Okay. This corresponds to j equals to 1. This corresponds to j equals to 2. This corresponds to j equals to 3. Know how much the energy? This is 0. This is 2b, because your energy formula is nothing but E of j is equals to b j into j plus 1 h cross. Okay. In terms of, if you are going to express this energy in terms of wave number, it is also the same. So your energy will be, sorry, if you are going to express in terms of wave number, so just a minute. The new bar will be b j into j plus 1. Okay. So if you are putting value 0, this will be 0. So for j equal to 0, the energy is 0. For j equal to 1, 1 into 1 plus 1, that is 2b. J equal to 2, that will be 2 into 3, successive numbers. For j equal to 3, 3 into 4, that is 12b. Now if you are going to calculate their difference, it will be difference will be, this will be 2b, this will be 4b, this will be how much, 6b, right? Now when you are getting this rotational spectra, they will show this transition 2b, 4b, 6b, 8b, like that. So what is the difference between these two successive lines? That would be 2b in each case. Okay. So what about your successive lines? Like if it is not 10th and 11, if it could be 8th or 9th, it will not depend upon J. It will be always 2B. The difference between these successive lines in the rotational spectrum, it should be always equals to 2B. Okay. So in this case, you can see what is the 2B value? The difference is 20 centimeter inverse. So I am going to put this 2B is equals to 20 centimeter inverse. Okay. So what should be my B? B should be 20 by 2. How much it will be? It will be 10 centimeter inverse. Yeah. So what should be the answer? That should be 10. And B is called also rotational constant. You have seen that. Okay.
Yes, sir.
Okay. Okay. So this is the fifth question. The first line in rotational spectra corresponds to B, 2B, 6B, 4B. I have explained that in the previous slide. So what should be the answer?
2B.
2B, yes, exactly. Because what I have written here that your difference of the first line in your rotational spectra, every line corresponds to this transition. Okay. Oh yeah. So in rotational spectra, suppose this is my j equal to 0 level, this is my j equals to 1 level, this is my j equals to 2 level, this is my j equals to 3 level, etc. So in rotational spectrum, what we can see is transitions. Sorry. Also you can see all these transitions. Okay. So what should be your the difference between this? You have seen what I have said that transition is allowed between the successive levels. That is, we need to follow this condition that delta j should be plus minus 1. So what will be the difference here? It will be 4b. What should be the difference here? It will be 6b, because you can see here this energy will be 0, this energy will be 2b, this energy will be 6b, this will be 12b. This will be 12b. So the difference in energy will be 2b, 4b, 6b. Now, whatever he has said here, that the first line, the very first line, the first line, what is the first line? First line corresponds to transition from ground rotational level, that is j is equals to 0 to j equals to 1. Correct? So your energy difference delta E, suppose okay, I am writing it in terms of nu bar, it's the same thing, just difference of unit of energy, nu bar will be the difference in terms of new bar. That is, what is the energy of this J equal to 1 state? This will be 2B. And what will be the energy of this ground state J equal to 0? This will be 0. So this will be 2B. So your first line corresponds to the transition which corresponds to 2B. So your correct answer will be 2B, and you have answered it correctly. Okay. So this is our sixth question. Which of the following lines are not allowed in normal rotational spectra? This 1 to 2, 1 to 3, 1 to 5, and 1 0 to 1. You can clearly see not allowed. Okay. So what should be the answer?
1 to 5.
Uh-huh. Only 1 to 5?
Yes.
Okay. So, so you can find this answer also in lecture number 15, where you can see the, okay, I'm writing in here below. Yeah. Your selection rule or rotational transition. Selection rule for rotational transition. What is the selection rule? That it needs to satisfy for a rotational transition. The selection rule is delta J, that is a change in the rotational quantum number, always is equals to plus minus 1. Okay. So this is the condition or selection rule, which is known as selection rule for the rotational transition, that your delta J, that is the difference between the successive between two rotational level, that should be equals to plus minus 1. When this is possible? This is impossible when their levels are successive levels, that is from 1 to 2, 2 to 3, 3 to 4, but not 1 to 4, 2 to 5, that is not successive levels. So only transitions are allowed where there is a transition from successive levels. Okay. So for each case, we are going to calculate delta J. So for option number 1, you can see the delta J, what will be the value of delta J? That will be 2 minus 1, right? Because the J in the 1, because delta J will be what I have said, the difference of the rotational quantum numbers between two states. So since it is a transition from state 1 to state 2, so this delta J will be 2 minus 1. So what is this? This is 1, right? Now you can see this transition selection rule. This is allowed transition, right?
Yes, sir.
Yes.
Uh,
Now
1 to 5 and 1 to 3 will come there.
exactly. Now for second one, you can see the transition will be always from 1 to 3. Okay. So your delta J, when you are going to calculate your delta J will be 3 minus, what is this? This is 2. Not equal to 0 plus minus 1. So this transition is not allowed. Now option 3. So I am going by option to show you that which transitions are allowed. So for option 3, the delta J will be how much? This will be always 5 minus 1, just like the other cases. It will be 4. It is also not satisfying the condition for rotational transition. So this will also not possible. This transition is also not possible or forbidden transition. Yeah. So number 4, delta J, there is a transition to 0 to 1. So delta J will be 1 minus 0. That will be 1. So since delta is equal to 1, this will be allowed transition. Now you can see here two transitions are allowed, that is 1 to 2 is allowed, 0 to 1 is allowed, but delta j is equals to not is equals to plus minus 1 for second and third option. So these two transitions are not allowed. And in question you can see which of the following lines are not allowed in normal rotational spectra. So you can clearly see that normal rotational spectra, which lines are not allowed? That is two lines are there. Yes, this 1 to 3 is not allowed, and this 1 to 5 it is not allowed. Other two transitions, that is your 1 to 2 transition and also 0 to 1 transition, these transitions are allowed. Okay, so your correct answer will be 1 to 3 and 1 to 5. Got it?
Yes.
Now I'm going to the next question, which is saying that the energy of a rotational level is given by 20 B centimeter inverse. So you have to find what is the degeneration. So you have four options: 7, 6, 9, 5. So what should be the answer? What should be the answer? So you know the formula of degeneracy.
2j plus 1.
How much?
2j plus 1.
2G plus 1. So to find the degeneracy, you need to calculate which one? You need to know the value of J, right? So if you know J, you can calculate degeneracy.
Yes.
Now, your trick is here that you are given the energy of a rotational level, which is given as 20 B centimeter inverse. So, by somehow, since from this one, you have to find the value of J. And this value of J, if you know the value of J, you will put it that in this degeneracy equation, it will show you degeneracy. So, you can find this reference. So, you know the energy Ej of a level J is given by this equation. Yes. So Ej is given as J into J plus 1 P. What is Ej? Ej is the energy of any jth level, jth quantum number level, any level with quantum number j, your energy will be Ej. Now, in your question, there is written as the energy of a rotational level. It is not mentioning which level it is. It is just mentioning the energy. It is written as 20 B centimeter inverse. So, your energy of any level, you can know this this one should be equals to 20 B, right? So your energy of any level J is given by this equation J into J plus 1 B. So you know that it is here it is given the energy of level is 20 B centimeter inverse. So I am just putting Ej equals to 20 B. Okay. So I am getting this equation J into J plus 1 B is equals to 20 B. So I can cancel B from both sides. So what I am left with? I am left with this J into J plus 1. This should be equals to 20. From that, this is the basic mathematics. J square, you have to find the value of J. Okay, this is the equation, and only single variable is there. Only one variable is here, which is J. Okay, From here, you have to find what should be the value of j. So I am just going to solve it. So j square plus 5 minus 4j minus 20 equals to 0, because there is something 1, so I can write it as 5 minus 4. So most of you know that. So this will be j square plus 5j minus 4j minus 20 is equals to 0. This gives, I can take j common from this first two term, j into j plus 5 minus, I'm taking 4 common, j plus 5 equals to 0. So which gives, I can take j plus 5 common also. So j plus 5 minus j plus 4, sorry, j plus 5 into j minus 4 is equals to 0. This is what I have derived from the here, that j plus 5 and into j minus 4 is equals to 0. Now I'm writing it here again. J plus 5 j minus 4 equals 0. Okay. So if you are sincere enough, you can understand, as whenever I have started solving this equation, you have seen there is a quadratic equation. Okay. That means the variable has a quadratic power. So it is there as squared. Okay. Since it is a quadratic equation, so you will get two values for this variable. So what are the two values? You know from here, two values you will get. If this is equals to 0, j plus 5 is equals to 0, you will get j is equals to minus 5. And from here, if j minus 4 is equals to 0, you will get j is equals to 4. So you have two j values. One is minus 5, another is 4. Okay. So let's delete it. J is equals to 4. So I've got two values of j. One is j is equals to minus 5, another is j equal to 4. Now you can see that since j is a quantum number, or which signifies the which state is it is, you cannot say something quantum number minus 5. So j not is equals to j less than 0 is not allowed, not possible. So you cannot take this value. So what should be your final j? The j will be 4. Okay. So now you can tell me what should be the degeneracy, because I have given you the value of j.
9.
Exactly. So since you have know the value of j, so the degeneracy you just need to put here, that will be 2 into 4 plus 1. So it will give you 9. So what will be your answer? The answer will be 9. Because, so how did I solve that? So I know the what should be the energy of a level with quantum number j, which is given by j into j plus 1 v. Okay. From that, if from that I have just equalized it with 20b. So this by 2b will be cancelled out. So I was left with j into j plus 1, which gives me 20, and I have solved this quadratic equation, and this quadratic equation gives me what I have the value of j is equals to minus 5 and 4. But the value of j equals to minus 5 is not allowed because j less than 0, you cannot define any state with value less than 0. So less than 0 value of j is not possible. So what will be my j value? My j value will be 4. Now I know what is my degeneracy. Degeneracy is given by 2j plus 1. So I am putting the value of j as 4. So it will give me 2 into 4 plus 1, which is given by 9. So my degeneracy will be 9. Got it?
Yes.
Yes. So now moving to the next question. You are given the rotational constant of HCl is 4x. Now you need to find what should be the rotational constant for DCl. So it will be 8x, 4x, 2x or x. Will it remain same or change? HCl to DCl. So hydrogen is replaced by deuterium. So this what do you say? This rotational constant will change or remain the same?
It will change, no?
Yes, it will
Due
change.
to
What will be the value?
8x,
Sorry,
8x.
8x. Okay, just a minute. I think you have seen this answer also. Okay, so I am explaining it. First, you need to know this is the question which was mentioned in lecture number 15 that in case of isotope, you can find the relation between these rotational constants for two different molecules. Okay, so when there is isotope, yeah. So for the case of isotope, you know this is my diatomic molecule. Suppose this is HCl. Suppose this is H, this is Cl. Okay. Whenever you are forming DCl, you are just replacing this your hydrogen with deuterium. You are replacing your hydrogen with deuterium. Okay. So the distance between H and Cl, that is internuclear distance or bond length, whichever you can say it, this will not change whenever you are replacing your hydrogen with deuterium. What change? Actually, the change will be in the mass because you know the mass of hydrogen and deuterium are not same. The mass are different. So this the HCl and DCl, whenever you are replacing hydrogen with deuterium, your mass will change. Now I have mentioned that for such cases, another term is used instead of mass, which is known as reduced mass. Reduced mass. You heard the term reduced mass? Yeah, reduced mass. Reduced mass is given by mu, which is defined as m1 into m2 divided by m1 plus m2. Okay, this is the reduced mass mu, which is defined as m1 into m2, where m1 and what is m1 and what is m2? M1 and m2 are the mass of the two atoms. Okay, in the case of HCl, m1 and m2 are the mass of H and Cl. In case of DCl, the m1 and m2 are the mass of D and Cl. Okay, this is the reduced mass. This will change whenever you are substituting some atom with its isotope. The change mainly that will be the change in the reduced mass. Okay, so R will not change. Now you know what is the moment of inertia. Moment of inertia I is defined as summation over I mass into Ri square. Hmm? So since your R will be not changing, so it will the moment of inertia will be different. Okay, so your moment of inertia will be completely different. It will since your mass will change. R is not changing, mass will change. So I will be different. Now to know that for the case of B, you know B is proportional to 1 by mu. If you see this energy expression, you can see if you are going to compare, you can see that in the equation B is equals to something by I. I will be always in the lower side. Okay. So since I is equals to mi square, or in case of this molecule that is mu r square, I should write it mu I ri square. Okay. Summation over I mu y ri square. So I can write it here. So I can say that B is inversely proportional to mu. So for your two isotopes, suppose I am leveling the HCl. Okay, I am leveling this HCl as normal B, and the all the terms related to this Cl I will denote by a dash. Suppose this is my B, which is B for HCl. So I am reporting that I will say that the it is B prime, the B prime denotes the rotational constant for DCl. Okay, and you know that this is inversely proportional to mu. So whenever this is in the numerator, then it will be mu prime on the upper side and mu on the opposite side. Okay, so if you are going to take the ratio, okay, then you can see that if B prime is in the here, then your mu prime will be in the upper side. Okay, so this is your relation. I'm writing it over here. B by B prime equals to mu prime by, okay, just a minute. Now to calculate, you need to find, what do you need to find? You need to find B prime, and you need to see how it is related to B, that is the rotational constant of ACL. So I'm just reversing it. So reversing it will give me B prime by B will be equals to mu prime, right? Just I am just rotating this both side. Okay, so the B prime will be mu by mu prime into B, right? You understand this much?
Yes.
Yes. Okay. Now what I'm going to show. So what do I need to find? I need to find which one? Mu prime, mu by mu prime. Okay. So I have to find the ratio of reduced mass of HCl and DCl. The ratio of the reduced mass of HCl and DCl. Okay. So that for that I will take another slide. Just a minute, because it is too much congested now. Okay. Yeah. So you got your B prime by B. I'm writing it again. So B prime will be is equals to mu by mu prime into B. Okay. So you have to find the ratio of mu by mu prime. So for this you need to find what is mu of HCl. Now as I have mentioned, this mu will be m1 into m2 by m1 plus m2. Okay. So for HCl, I am just replacing these terms: mass of H, mass of Cl, divided mass of H and mass of Cl. Now you know everybody knows about mass of H. What will be the mass of H? What will be the mass of H?
One.
Everybody knows that. Yeah, 1. And what will be the mass of Cl?
35.5.
Hmm?
35.5.
35.5. Okay. Now you need to remember something. So what is the unit? What should be the unit?
AMU.
The unit will be this mass unit will be kg per mole. Okay, or kg mole inverse, whatever you want to write. So this is the mass of 1 mole. Okay. So to remove this 1 mole, you need to divide it with Avogadro number. Okay. So whenever you are dividing it with Avogadro number, this will become only kg. Good. Similarly, when you are mass of 30.5, this mass of chlorine, when you are dividing it with Avogadro number, it will become 35.5 by Na kg. Okay. So this is your mass of hydrogen. Because how this is happening? Because Na is the Avogadro number 6.023 10 to the power 23 mole inverse. Okay. So your mole inverse will cancel out. You will get only the value of mass in kg. Okay. Now you are just putting these values. Mu of HCl. I'm not writing the value of Na because why I'm not writing you will see later. So I'm just replacing it here. So 1 by Na into this 35.5 divided by Na divided by mass of hydrogen will be there. That will be again 1 by Na plus 35.5 divided by Na. Okay. So I should write it 35.5 35.5 by Na square into, I'm just separating this numerator and denominator, and the lower one will be 1 by 36.5 by Na, right? Because the 1 plus by Na plus 35.5 by Na, this will give you this Na will be the LCM and it will give 1 plus 35.5. So it will give you 36.5. Okay. So my final expression will be 35.5 divided by this Na square into what should be Na by 36.5. So 1 Na will be cancelled out. So we will be left with 35.5 by 36.5 into 1 by Na. So what should be the unit? You need to write the unit. You can see here what unit I have used. There is a kg. Yeah. So here is a kg for 1 by Na, which is the mass of hydrogen. And another 35.5 by Na is the mass of chlorine. So these will another kg. These 2 kg will multiply to give me kg square. And here I am adding just 2 kg. This will give me just only kg. So my final unit will be only kg. You got it?
Yes.
Yes. So this is the value of reduced mass of HCl. Now you can see I am not further calculating it or not further simplifying it. Why I am not simplifying it? You will find it later, because there will be some benefit if you are not going to solve it now. First, you need to know the new value of PCl. Yeah, so I'm calculating mu of DCl here. So by the same formalism, we just use MD into MCl divided by MD plus MCl. Okay. So what should be the mass of deuterium? What should be the mass of deuterium?
2.
2 unit kg per mole. Okay. So when you are going to convert it to just kg, it will be how much? 2 by Na. When Na is the Avogadro number, so this will be 2 by Na kg. So what should be the mass of chlorine? Mass of chlorine will be 36.5. Sorry. This will be 35.5 by Na, right? So in my mu DCl equation, I'm gonna write 2 by Na into 35.5 by Na divided by 2 by Na plus 35.5 divided by Na. Cool. Next, what should be the, now I am going to, is 2 into 35.5. I'm just going to write it like this. Okay, divided by Na square into, just like the previous one, this upper one will be added up. It will give you, I'm just getting a steep jump because the same thing will happen here. This will be 37.5. Okay, the same thing here you have seen this 35.5 plus 1, this will give you 36.5. The same thing here, 35.5 plus 2, this will give you 37.5. And this Na will be revert back, it will go up to the upper one. So there is Na square in the denominator, and so it will cancel out 1 Na. So you will be left with 2 into 35.5 divided by 37.5, this whole term into 1 by Na. This much kg the same way. You have to calculate. You just put the values, this O upper in the upper side, this kg will multiply, this will give you kg square, and in the lower side this kg and kg will add up, this will give you kg, and this kg will, 1 kg will cancel out, so it will give you kg. So you have got this is the, what is this? This is the mu of, this is the reduced mass of this here. Now you have got two different things, which is reduced mass of HCl and reduced mass of DCl. Okay. Now, yeah, I'm just writing. So I need to find first what is my mu by mu prime. So I am writing this mu. This is 35.5 by 36.5 into 1 by Na, this much kg, and divided by, should have written here, sorry, so mu by mu prime, this should be, so I'm plotting the value of mu 35.5 by 36.5 into 1 by Na kg, and I'm now writing the value of mu prime, which is nothing but 2 into 35.5 divided by 37.5 into 1 by Na kg. You see, I am not used, I am not simplified that, I am not multiplied this 35.5 with 2 because of some reason, and you will see it now. Your kg will cancel out, 1 by Na in the both sides, this will cancel out. Okay, so you are left with what? You are left with is 35.5 divided by 36.5 into, this one will be 2 into 35.5 into, here will be 37.5. Good. So your 35.5 also will be cancelled out. That's why in this case I told you not to simplify this, because this 35.5 will be cancelled out. So you will left with, I'm just writing it simply so that you can understand the next step. Half into 37.5 in divided by 36.5. Right? I'm just taking this two out. You are left with these two terms, 37.5 and 36.5. Now you can see its value. I don't know actually what is exact value. I'm not interested also. Can also see that this value is almost equals to 1. 37.5 divided by 36.5. This is almost equals to 1. So the value of mu by mu prime will be almost equals to half. Okay. So your value of mu and mu by mu prime, this will be almost equals to half. Now, what was your original equation? This was your original equation. Okay. You just need the value of mu by mu prime to know what is the rotational constant for DCl. You can find it. So your B prime will be, what is the value of mu by mu prime? You have got 1 by 2.
Half.
Yes,
Mm,
half into B, that is B by 2. So if you know B, you can find B prime because B prime is equals to B by 2. What is your B? It was mentioned in your question that you have a rotational
4.
constant of HCl is 4x. So a 4x is the value of your B or HCl system. So you have to put that value. So we'll end up just putting the value over here. You will end up B prime will be 4x by 2. So which implies B prime will be equals to 2x.
2x.
So what should be the rotational constant? This will be 2x.
2x.
Exactly. You understand how have we solved this?
Yes.
Okay. So in such problems, when you are facing that the same thing, that you have to find the ratio of your rotational constants. In some cases, you need to find out the ratio of this mass, reduced mass. Then your B and B prime will be given. You can easily calculate that. But for the cases where you have to calculate B prime, you not need to know mu. And be alert that when you are calculating mu, this mass will be your the mass what you have learned. This is a mass in kg per mole. To convert it to kg, you need to divide it with Avogadro number. Okay, and then you just use this formula that mu is equals to m1 m2 by m1 plus m2. Upper one is multiplication and the lower one is division. Sorry, lower one is addition. So in that case, you can find these two mu. You take the ratio of these two, and you will find p and b prime ratio. And from this, what you will need to calculate, you can easily calculate. Okay. Okay. So moving to the next question. So it is mentioned here that allowed values for the rotational number m1 is -2, -1, 0, 1 and 2. So what should be the energy of that rotational level? It will be 4b, 6b, 8b, 10b. What should be the answer? You remember the question which was mentioned as you have to find the degeneracy, for which you need to find the value of J, right?
2j plus y.
Yeah, that was your degeneracy. In case of degeneracy, you need to find the value of J, and then from you can calculate your degeneracy. Same thing will happen here when you are asked to find what will be the energy of your energy level with rotational quantum number J. You know this, that the value of J will be given as J into J plus 1 B, right? And you have seen that all of your answers, all the options is given here, it is given in terms of B. So you don't need to find B. What you need to find? You need to find is only parameter J. Again in this case, you have to find the value of J. Okay. If you know J, you can calculate EJ. Which energy level? So first you need to know J. So this is the explanation. So these M values. Do you know about azimuthal quantum numbers?
No.
Principal quantum number? Do you know about SPDF orbitals?
Yes.
Then you need to know azimuthal quantum numbers, right? Which is denoted by L. You know L? L is equals to 0, it corresponds to your s orbital. L equals to 1, it corresponds to your p orbital. That is the azimuthal quantum number. Okay. So this L is called azimuthal quantum number. So upon basis, why I'm using this one in this case, it is relevant. I will explain you that in case of azimuthal quantum number L, how many states could be possible? This is from minus L to plus L. So this is minus L plus L. So what is the significance of these states? These states, when the molecule is in a magnetic field, there will be the splitting of this L level. They will split into this much levels. There will be a 0, minus L to plus L, and there will be a 0 level. So these values are called ML values. Okay, magnetic quantum number. Under magnetic field, these L values will be splitted. Suppose my L value is 4. L is 4. So under magnetic field, you will have value from minus 4 to 0, minus 4 to 0, and then you will be up to plus 4. So how many values will be there? Minus 4, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, plus 4. Okay, so you can count that. It will give you 9 values. Okay, so for any L level, L equals to 4 here, in case suppose I have taken this L equal to 4, you can see that number of J values, number of ML values will be 9. So such cases, for any value of L, you can see that from minus L to plus L, what I mentioned. So ML values will be ranging from minus L dot 0 dot plus L. That means from minus L to plus L, there will be another 0. So how much values are there? There from minus L to 0, there are L values. From 0 to L, how much values will be there? There will be another L values. 0 to 5, how much value will be there? 5 values. 0 to 10, how much values will be there? 10 values. Rather than 0, okay? Other than 0. So there will be 10 values. So you will have L plus L, there will be 12 values. And another value is 0. This is another value. So how many values will be there? 12 plus 1. So for any L, there will be 12 plus 1 ML values. These magnetic quantum numbers will be 12 plus 1. You can easily correlate these with your degeneracy, right? Your degeneracy, what your formula for degeneracy? 2G plus 1, right? Just the same thing you can see here. It is 12 plus 1. And here you are mentioned the rotational numbers, allowed rotational numbers are minus 2, minus 1, 0, 1, and 2. Minus 2, minus 1, 0, 1, and 2. So how many numbers are there? 5 numbers. Okay. So total 5 numbers. So you can easily relate that this is nothing but your degeneracy, because this rotational number m1 is the values of this quantum number signifies that for one j states, how many states are there which have the same energy as this j state. So you can find this as 2j plus 1. So it is, so in this case, since there are 5 in numbers, so I can write this 2j plus 1 as 5. So little simplification will give me j only equals to 4, which gives me j equals to 2. Now I have got the value of j. Okay. So from rotational quantum number, I have to calculate how much values of rotational quantum numbers is given. Okay. So I know that this number of values will be 2j plus 1. This will be the degeneracy. So I have just equated that 2j plus 1 will be equals to 5, and then I have solved for j, and I have got the j value is equals to 2. Now I have to find. I am not finished then, because I have to find this energy. This energy will be given as J into J plus 1 into B. Now you have to put the value of J here, 2 plus 1 into B. So 2 into 3, this will give you 6. So what will be your answer? Answer will be 6B. You got it? How to calculate this?
Yes.
Okay. So your answer will be, answer will be 6B. Okay, so in that questions, when you are given this value of mi or m1 or ml, anything, m kind of thing, you can see here there is a sequence. Suppose it was from -4 to +4, -4, -3, minus. Okay, I'm taking 4 too much, so I'm taking -5. Suppose -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. So in that case, what should be your value of energy? You can calculate that, because from -5 to +5, how many values will be there? There will be 11 values, including 0. -5 to -1, 5 values. +1 to +5, 5 values. And 1, 0. That will be total 11 values. Okay. So you need to just put your 2j plus 1 will be equals to 11. Okay. And then from that you can calculate your j. You can put that value of j in this equation of energy. You can find what is the energy. Okay. So this is the last question where I'm going to solve today. That given that HCl molecule has a bond length of 1.27 angstrom. Suppose we have a molecule of HCl which is a bond length of 1.27 angstrom. Now, if you increase the bond length by 10%, keeping the mass constant, so what will be happen to moment of inertia of HCl? Will it increase? Will it decrease? Will it remain same? And also, not enough information is provided here. So I think for your simplification, I am just saying that enough information is provided here. So can you say if it will increase, decrease, or remain same? So I am just simplifying it for you again. This is the formula of moment of inertia, right? Now you
It
can
will
easily calculate.
increase.
Huh?
It will increase.
It will increase, exactly. In such questions, you can see that no particular value is mentioned here. That is, you need not ask to calculate the value. Just you need to give the qualitative information that whether it will increase or it will decrease. So you know that moment of inertia is defined by I equals to mi ri square or mu I ri square. Okay. So I'm taking this mu I ri square summation of I by ri square. Suppose now, suppose after increase in bond length, here it is mentioned that your bond length of HCl is increased by 10%, R becomes R prime. Suppose. Don't confuse it with the isotope case. Okay, this is a completely different case. I'm supposing that my initial bond length was R. After the increase of the bond length, what it is mentioned here, that after increasing the bond length, this R is become R prime. Okay. So if you want to take the value of R as 1.27, and if you want to just increase it by 10%, you can easily do that. Okay, this is also the correct formalism. But since you were asked with the qualitative information, I am just qualitatively explaining this. So, what will be your mu? Since your R becomes R prime, so what will be your mu?
Mu is constant, no?
Exactly, mu is constant here. Where is this? Yeah. So it has written here that your mass is constant. So your mu is not changing. Mu will become not mu prime. This will be not mu prime. Mu will remain. Yeah. Now it is mentioned that I is equals to, suppose your moment of inertia will change. It will become I prime for elongated case. Suppose you are want to elongate this ACl molecule. Suppose it is elongated form, in elongated form. So your moment of inertia in the previous case, what was I, it will not be I again. It will, suppose I'm taking it I prime. Your mu is not changed. Your Ri will be changed as Ri prime, but the square will be there. Yeah. So your I prime will be mu by Ri square. Suppose I'm just interested in Ri. Since I know that mu is unchanged, okay. So okay, you can do it another way. So anyway, so suppose since I am taking this I equals to 1 here just, so yeah, so I prime is equals to mu r prime square. Okay, so what is your r prime? R prime is 10% increase of r. Suppose your r was uh, r, then it will be increased by 10%, right? All right.
Yes.
Yes, because suppose you have 100 rupees, I am saying that your money will be increased by 10%, so it will become 110. So this R will be R plus 0.1 R, right? You know this one. So what will be the value? 1.01 R. Okay. Sorry, I made a mistake. This will be not 0.01, it will be 1.1 R. Yeah. So this will be 1.1 R. So what is your R prime? Your R prime is 1.1 R. Now you just need to replace this R prime with R. So when you are replacing this mu into 1.1 square, because you can see that in R prime there is a square term. Okay. So when replacing this, you know the square of 11 will be 121, and this 2 point will be just shifted where it will come out as this one. You can calculate this into, this will be mu, this will be R square. Now what should be my mu R square? What was my mu R square? Mu R square is nothing but just I. So I'm writing it here. So I'm getting my I prime will be 1.1 times I. Okay. So I'm writing it clearly because it is a very fundamental relation that your, if you increase your bond length by 10%, your moment of inertia become how much percentage, can you guess? It will increase by about 21%. So if you want to increase your bond length, your moment of inertia will be 1.21 times your previous value. That will increase. In qualitative language, you can say that your moment of inertia should increase. Understand?
Yes.
Okay. So have you any doubt up to this?
No.
No. Okay, fine. Okay. Okay, fine. So I need to stop the recording because it's the session is over already. Okay. Okay, fine. Are you a BSc student?
Yes.
Which